Imagine standing in a dense forest, but instead of familiar greens, every leaf and every blade of grass is a deep, vibrant crimson. You are 500 light-years from home, standing on the fifth planet of a distant solar system. Welcome to Kepler-186f. Astrobiologists have spent years analyzing this specific world because it checks many of the exact boxes required to be humanity's next potential home. The surface conditions are remarkably welcoming. The ambient temperature here closely mirrors the comfortable, mild evening climates we enjoy back on Earth. Curious, but if the climate is so recognizable, why does the native biology look entirely alien? What drives an entire ecosystem to grow in striking shades of red? Kepler-186f is a world of conflicting traits. It offers the warmth of an Earth twin while operating on completely different biological rules. To understand how that happens, we have to look up at its sun. The engine driving this entire solar system is a specific classification of star known as a red dwarf. This compares a standard yellow sun to a red dwarf. Kepler-186f star burns roughly 2,000 degrees cooler than ours. Because of this, the luminous energy reaching the planet drops significantly, receiving just 32% of Earth's light. A restricted low-light environment poses an immediate crisis for any native plant attempting to gather energy. Standard green vegetation simply wouldn't survive in this perpetual twilight. The host star always sets the rules. A cooler sun forces nature to completely redesign the biological machinery of how life gathers energy. Photosynthesis is a highly adaptable process. Plants don't get to choose their light source. They have to work with whatever spectrum of radiation hits their leaves. The meager light trickling down to Kepler-186f is heavily skewed towards specific wavelengths. Vegetation here had to develop a highly efficient workaround to avoid starvation. This world's vegetation evolved crimson pigments to maximize the capture of incoming blue light rays, while reflecting red ones away. By absorbing these opposite-colored rays, the plants process photosynthesis at peak efficiency, extracting every drop of energy. The deep crimson forests here aren't a random cosmetic choice. They are a highly calculated biological adaptation to a cool star's faint glow. Biology is only half the equation. The other half is the physics of actually trying to get there. Right now, humanity's absolute technological limit for space travel caps out at a top speed of 163 kilometers per second. That speed sounds impressive until you stack it up against 500 light-years of empty space. This visualization tracks a human life against that distance. At 163 kilometers per second, a one-way journey to Kepler-186f would take 9.2 million years. That timeline is an insurmountable barrier. It renders physical colonization of this planet functionally impossible for modern humans. This illustrates the brutal tension in exoplanet research. A world can have the perfect temperature and a thriving ecosystem on paper, while remaining mathematically out of reach in practice. But even if we could cheat the physics of travel, there is one final flaw in the Kepler-186f colonization dream: our total ignorance of its atmospheric composition. We can calculate light, and we can measure temperature, but scientists currently possess no accurate estimate of the specific gases that actually form the air on this world. Imagine a generation ship surviving a 9.2 million-year journey through the void, only for the descendants to arrive and find the atmosphere entirely toxic and unbreathable. If you want to keep exploring the hard realities of deep space and the actual science behind these distant worlds, make sure to subscribe. Ultimately, Kepler-186f serves as a reminder of how exceptionally rare our own Earth is, a prompt to protect the only habitable zone we currently possess.